Okay, so for the beginning, we are going to continue from where we stopped yesterday. So yesterday we stopped at essay question number 4. So essay question number 4 sounds like this. Different standard enthalpy change of formation for sulfur dioxide, 2 marks. Standard enthalpy change of formation for sulfur dioxide and sulfur trioxide are negative 183.0 kJ per mole and negative 297.0 kJ per mole respectively. Construct an enthalpy cycle and calculate the standard enthalpy change of combustion for sulfur dioxide. Okay, so in here you have to know on how to define standard enthalpy change of the combustion formation. So enthalpy change of formation is the heat change or energy change when 1 mole of sulfur dioxide is formed from its element, first mark, under standard condition, second mark. Okay. I repeat, the 2 points in here usually is you have to define the heat change or energy change when 1 mole of sulfur dioxide is formed from its element, 1 mark, and then under standard conditions. So all the 10 enthalpy change, I already asked you all to memorize one by one. And then if possible, you might want to attach the equation together. But in this case, not necessarily, because the B1 questions will also need you to write equations. Okay, so there we go for B. So you need to understand how to write the equation of combustion for sulfur dioxide. So you must know when sulfur dioxide burns, it will further oxidize to become sulfur trioxide. Okay, so the equation, the question purposely do not want to give you the equation because the equation itself has marks, because 7 marks in here is actually quite a lot. So you should be able to write out all. So the best way to get the full 7 marks in this is by using Hess law. And as I always mention, whenever you're applying Hess law, you should always first write the equation. So state of matter is a must. State of matter is a must. So S plus O2 give SO2, and then S plus 3 over 2 O2 give SO3. So this is their respective enthalpy change. So towards that, so all you need to do is just reverse the first equation. This one no need to multiply by 2 because you want to calculate. My bad, sorry, because I made a mistake in here. It's not SO2. Oh, wait a second. Is the notes in here is SO2 or not? I'm worried if I copy paste the wrong things inside here. No, they didn't mention. Okay, so it's my fault. Okay, so because I uses the 2. Okay, so I'm going to correct it here. Okay, you just use the standard enthalpy change. Right? So this one is negative, positive 183. And this one is negative 26. Okay, so sorry, my bad for making such a grave mistake. Okay. So this will be negative 114. Okay. Then the energy cycle also is wrong. Later I will reconstruct. Okay, sorry for that. Okay, so you just reverse the first one, and this is your answer for it. Okay, so how are we going to construct the Hess cycle in here? So I'm going to show you one by one. So in here, eventually you can notice that between here you can cancel sulfur, cancel with sulfur. So this one is 3 over 2 O2. Sorry, so half O2 cancel with 3 over 2 O2. You get half O2 left. So this is your overall equation. SO2 plus half O2 give SO3. Delta H is negative 114.0 kJ per mole. Okay, so how to construct the Hess cycle in here? So as usual, you always put in here the y-axis and then label energy. Okay, in kilojoule. Okay, and then we'll put the line in between. So this is the line. Okay, so I'm going to so the first one is the largest one, which is the 297. Okay. So this one, okay, this is how sulfur becomes sulfur trioxide. Okay, this is the formation for the sulfur. So you have S solid plus 3/2O2. Okay, give SO3. Okay, so this one is negative 297. And then in here, the next energy level is for the formation of the SO2. So you must first form SO2. Okay, so the SO2 is negative 183. Okay, so this one is SO2. Okay, so don't forget, not all oxygen is used for the reaction. So there are some remaining SO2 left. So you have to bring down the half oxygen in here. So this is the oxygen unreacted. Okay. Then finally, for SO2 to become SO2 plus O2 to become SO3. So this one is negative 114. Okay. So very simple energy level diagram for you to construct in here. So I hope that you'll be able to learn on how to construct the enthalpy cycle for these reactions. Okay. Okay. So with that, that is how you solve for question number 4B1. Okay. Immediately we move to the next one, which is 4B2. So number 2, compare the relative stability of SO2 and XO3. Explain your answer. So as I already mentioned in our lessons, so you enthalpy change of formation can use to predict which substance is more stable. So the one which is the more exothermic is more stable. So eventually, evidentially, SO3 is going to be more stable than SO2. So why? Because the enthalpy change of formation of SO3 is more exothermic than SO2. So equilibrium tends to shift more to the right. Okay, so that is how we are going to explain why SO3 is more stable than SO2. You can also make use of the reaction SO2 plus half of the O2 give SO3 is also an exothermic process. But usually, in this case, we usually compare using enthalpy change of formations to compare the relative stability. Okay, so hope you'll be able to compare the reactions in here. Okay. Okay, C. CO react with zinc metal to form a stable complex of ZnCO4. The thermochemical equation for the reaction is shown below, where you have Zn plus 4CO gives ZnCO4. Delta H is negative 712.5 kilojoule per mole. So estimate the average bond energy for ZnCO in the complex. So in here, what is the question trying to ask in here is, because you want to form the complex of ZnCO4, so the ZnCO4 will look more or less like this. Okay, so you form the complex of ZnCO4. Okay, so this overall equation is 712.4. Okay. So now, what happens if the equation now is reversed? So if the equation now is reversed, that means ZnCO4 broken to become Zn plus 4CO. So the average bond energy in here is actually, after you get this enthalpy change, you have to divide by 4. So because this is due to the formation of the complex. So when the complex dissociate, breaking down, don't forget breaking the chemical bond absorb energy, which is an endothermic process. So when you reverse the equation, magnitude is still the same, but vector changes, and then you have to break to become 4CO respectively. So because they want average bond energy, so eventually you have to you have to divide the number by 4. Okay. So in here, so number of ZnCO4 is 4. So bond energy is equals to positive 712.5 divided by 4. You get positive 178.1 kilojoule per mole. Okay. So this is how we are going to solve for question number 4. Okay. So any questions so far? Which part in here they cannot understand would like me to repeat for you? Okay, so no problem. We move to question number 5. Okay, question number 5 sounds like this. Standard enthalpy change of benzoic acid is commonly used as the standard calibrating constant volume bomb calorimeter. Its value has been accurately determined to be negative 3230 kilojoule per mole. When 1.98 grams of benzoic acid are burned in calorimeter, so the temperature rise from 21.5 to 27.8. One, calculate the heat capacity of the bomb calorimeter. So in here, you must be very good in calculating the heat capacity by using the three-step methods. What are the three-step methods that I mentioned? Number one, Q equals to C theta. Then number two, you have to find the mole is equals to mass divided by the molar mass. And then finally, number three, delta H is equals to Q over mole, isn't it? So now you use the reverse method. So when you use the reverse method, then you'll be able to get accordingly. Now, it is always safer if you first write the equation for the combustion. Okay, always try to write the equation for the combustion. Don't care where the marks located, because as a student, you don't care, you don't go and predict the mark. You just try to write whenever you can. Okay, so so mole of benzoic acid is equals to 1.98 divided by 132, which is 0.01623 mole. And then Q is equals to delta H times mole. So 3230 kilojoule multiplied by 0.01623, or you get 52.4 kilojoule. So we're still in kilojoule. And then heat capacity is equals to Q over mole, where you have 5254 kilojoule divided by the temperature. You get your heat capacity as 8.32 kilojoule per degree Celsius. So in three significant figure, how do you know that? 1.98, 3230, 21.5, 27.8, all of these are trying to tell you that your final answer should be in three significant figures. Okay, number two, the same calorimeter is used to determine enthalpy of combustion for propane 1,2-diol, CH3CHOH, When burning 2.00 gram of propane 1,2-diol in a calorimeter will raise the temperature from 21.8 to 25.7. Calculate the enthalpy change of the combustion for propane 1,2-diol. Okay, so in here you have to calculate what is the temperature, what is the enthalpy change of combustion for this. So you use the step 1, 2, 3 back. So we have Q equals to C theta, or Q equals to 8.32 times 25.7 minus 21.8, or you get 32.45 kilojoule. And then mole is equals to 2.00 divided by 76, you get 0.02632 mole. And then delta H is equals to 32.45 divided by 0.02632. So you get your answer as negative 1230 kilojoule per mole. Also in three significant figures. So the 2.00 gram is already trying to tell you that your final answer should be in three significant figure. Okay, so that is how you're going to do for number 5. Okay, then we shall do for question number 5b, if you are ready. Okay, standard enthalpy change of the propane 1,2-diol, carbon dioxide, and water are given below. This is it. So this is the substance, okay? So using Hess law, calculate the enthalpy change of combustion for propane 1,2-diol, 5 marks. So in here, you should be able to write all the enthalpy change of formation equation. So for carbon, C plus O2 gives CO2. State of matter is a mass as usual. And then H2 plus half O2 give H2O. And then 3 solid plus 3 carbon plus 1 oxygen plus 4 hydrogen give the propane 1,2-diol. So you get negative 841.0 kilojoule. So in here, combustion mass, so you reverse the equation 1, reverse equation 3. So in here, so this one you multiply by 3, water you multiply by 4, this one you just reverse. So after you do the calculation, you rewrite all this one. So it is always wiser if you can get this one. Okay, so 3 times negative 395 plus 4 times negative 286 plus positive 841. So at the end, you get negative 1482.7 kilojoule per mole. Okay. Okay, so in here, how do you compare and explain the differences of answer in A1 and A2 and B1? So A2, because it's done in experiment, it's a bomb calorimeter, it's experimental data. And then B1 in here is theoretical value, because you calculate from the standard data. Okay, so it is expected that the A2, which is the practical value, is smaller than the B1, which is theoretical value. So why? Due to maybe incomplete combustion, some heat is released to the surrounding, different initial condition, because standard condition is 25 degrees Celsius, 1 atmosphere, isn't it? And if you look back at our information, we start at 21.8 degrees Celsius, which we do not start at the standard temperature, okay? Standard condition. So that is why it might be a little bit off from the original value. So that is why that the data in here may not be the same in here. Okay. Okay. So with that, that is how you solve for question number 5. Okay. So is there any questions that you want to ask? So if possible, in the Hess law in here, try to show the methods inside there. Okay. Okay, so if no problem, then we go to the final essay question, which is essay question number 6. Sodium oxide Na2O is a white crystalline solid with high melting point. Use the data below, construct a Born-Haber cycle, hence calculate the lattice energy of the sodium oxide Na2O. So we are given enthalpy change of the formation of sodium oxide, enthalpy change of atomization of sodium, enthalpy change of atomization for oxygen, first electron affinity, second electron affinity, first ionization energy, second ionization energy. So all the information is already given in the tables. So you should be able to construct Born-Haber cycles in here. So just construct Born-Haber cycle. So first, let's together calculate the lattice energy. So we know that to calculate lattice energy, we use the formula enthalpy change of formation is equals to enthalpy change of lattice energy plus the summation of everything. So because our reactions involving 2 sodium, so it's 2 times atomization and 2 times first electron affinity. So for the oxygen, it's first electron affinity plus second electron affinity. So eventually, when you manipulated the equation, the enthalpy change of the lattice energy is equals to -416 minus of everything here. So press your calculator, you get your final answer as -2574. So I hope that you get the same answer as I do here. So this is the lattice energy for the sodium oxide in here, okay? And then how to construct the Born-Haber cycle, as you already know, okay, if possible, try to put the axis in here as 0, okay? You must put 0 in here. Okay, so 0 kilojoule. So you have the 2 times atomization of sodium, 2 times first electron affinity, ionization energy of sodium, then you have atomization of oxygen, then you have first and second electron affinity. You can write in one shot, never mind. And then this is the lattice energy of Na2O. And this is the enthalpy change of formation for Na2O. So I hope that you'll be able to construct proper Born-Haber cycles in here using suitable diagrams. So try your best to be able to do all that. Okay. Okay. So with that, that is how you construct the Born-Haber cycles in here. Okay. Okay, so try to practice the Born-Haber cycles, then you'll be able to get your answer correctly. Okay, so with that, that is for essay question 6A. Then we go to 6B. Compare and explain the lattice energy of Na2S compared to Na2O. So in here, you should have, since S2 minus has a greater ionic radius and O2 minus. So we say that, isn't it? We say that the lattice energy is directly proportional to the charge, yet inversely proportional to the inter-ionic radius, isn't it? So we know that S2 minus has a greater ionic radius than O2 minus, and they have the same charge. They have the same charge. So the only factors that influence them is their ionic radius. Okay. So Na2S has a lower lattice energy than Na2O because of the lower energy, lower ionic radius in here. Okay. Okay, C. Using electronic configuration of sodium, explain why the second ionization energy of sodium is much greater compared to the first ionization energy of sodium. Okay, so the sodium has the electronic configuration of 1s2, 2s2, 2p6, 3s1. So the question already said use configurations. So you have to write out electronic configurations. So first electron energy is low since the electron is removed from a 3s orbital at the outermost shell. Okay, so that if possible, write the equations. Where the equation in here is Na gas, give Na plus gas plus E minus. Then from here you can explain. So now Na plus gas, Na plus is 1s2, 2s2, 2p6. Okay, so in here, second electron is removed from an inner shell with octet configuration. So that is why Na plus has a higher effective nuclear charge. So that is why you have you require much energy to remove the second electron from the sodium in here. Okay. Okay, so with that, that is all for the discussion of the essay question for the chapter 1. So I hope that you have learned on how to solve the answer accordingly. And if you need any revisions, you can always revisit to the YouTube that I already shared with you. Next week, we are going to discuss for chapter 2. So during these 3 days, Friday, Saturday, Sunday, so try to finish the all the objective, structure, and essay question for it. Okay, so with that, that is all for our lesson today. So see you all next week. Okay, so have a nice week.